All right. I've decided to make a video about the repeated eigenvalue case for a second order constant coefficient homogeneous ODEs. So here's our second order constant coefficient homogeneous ODEs. And to ensure that I've got the repeated eigenvalue, I'm going to set C equal to B squared on 4. So when I proceed through our usual analysis, where we substitute y equals e to the lambda t, we get lambda squared e to the lambda t plus b lambda e to the lambda t plus c e to the lambda t equals 0. So obviously we can divide out that e to the lambda t. Because I know what c is, I can substitute, and I have the following. So I can now go ahead and find my lambda. So instead of my usual 2 solutions for lambda, I actually only have one and it's repeated. So unfortunately, our general solution is then something like a to the power times e to the power minus bt on 2. Now, whenever we've done this in the past, we've had a second solution here, and we don't have that at this point. We need 2 solutions because we've integrated this ODE twice, right? Or we expected to integrate this ODE twice because it's a second order ODE. So a solution, a general solution, must contain 2 constants of integration, and so it must sort of contain 2 parts. Obviously, we can't just go and add, we might try just repeating our solution, of course. We can say a times e to the minus b on 2 plus big B e to the minus b t on 2, but that's obviously just equal to some other single arbitrary constant times this one functional form. The difficulty is that we've only got one functional form, one E type function, and we're stuck, right? We need a second one. So we could just repeat, try another guess, right? Ultimately, this was a guess. So we could guess again. What we're going to try is a sophisticated guess. Try guessing y of t equals to some function v of t times e to the minus b to t. Right, so what we've done is we've taken the solution we just found, we multiplied it by some unknown function, And we're going to try and find out whether this can solve the ODE. This v function is to be determined. We're going to choose v so that it solves so that we have a full, complete solution of for y. So the only two pieces of information we have are this guess and our ODE. So let me rewrite our ODE just for reference. C equals b squared on 4. So we've got our guess and we've got our ODE. That's all we've got. All we can do is substitute in and see what we can find out about v. Now, obviously, we're going to have to differentiate y once and twice. And to do that, we're going to use the product rule. So when we come to differentiate y, we differentiate v and leave the e stuff alone. So that's going to give us dv dt, because we don't know what the derivative is yet. We don't know what v is yet, so we can't really differentiate it properly. Plus, we leave v alone and differentiate the exponential term. In this case, that's going to give us minus b on 2 times v of t times e to the b t on 2, right? That's just the product rule. Now we have to do it again. We've got to differentiate this term. Then we've got to differentiate this term. And both times we're going to have to use the product rule. We're going to have to use the product rule on the purple term and on the yellow term. So we differentiate the first function, leave the second function alone. dv dt differentiated again just becomes the second derivative of v. When we differentiate the e term, we're going to get a minus b on 2 out the front. The e otherwise stays the same. Now we've got to start differentiating the yellow bit. I'm just going to clean this up a little bit so it doesn't get confusing. This one, so that's where I've differentiated the v, and now I've got to differentiate the e. So when I differentiate the e for the second part of the product rule, I'm going to get another factor of minus b on 2. That's going to come down and multiply that one to give me a b on 4 and a plus sign, importantly. Okay, now I'm ready to substitute this in. So I'll just keep track of my terms. That's why I did the colors in the first place. The purple box came from the purple part. Stuff in yellow came from the yellow part. All right, so let's plug in. That's the second derivative. Now I've got to take care of, oops, it's only half the second derivative. That's the second derivative. Now I've got to take care of the first derivative. This isn't particularly difficult. It's just tedious. It's tedious to keep track of all the terms. And then finally, I've got the y term itself. So just to keep track of all the terms, so you can see where everything's coming from. That's substituted this guess into our ODE. So obviously there's a common factor of e to the minus b on 2t that can just disappear from this. And I can start simplifying. So I'm going to do that, and I'm going to group up some terms that might not look all that obvious just yet. Just zoom in a bit. So this term here and this term here, they're pretty similar, so I can actually add them up. I promised that these would go away, so let's get rid of them now. Let's just make sure all my terms are actually there. I've forgotten this b. Let's put that back in. And we also note that we've got some simplifications we can make. So let's number all of these terms so we can keep track of them. 1, 2, 3, 4, 5, and term 6. There's nothing much we can do with term 1. It's the only second derivative that appears, so it's not going to simplify in any way, shape, or form. So we can write that one down. However, there's a first derivative term in 2 and 4, and we can combine them. So we've got minus b dv dt plus b dv dt. And that's term 2 and term 4. Then we've got term 3, 5, and 6. So this is from term 3. That b goes in there, makes that a b squared, and that's term 5. And that's term 6. Okay. Term 4 and term 2 obviously cancel. I can add up terms 3 and 6, and then I can subtract off term 5, and we see that this one's 0, 2. Right, so after all of that effort, we have found the following ordinary differential equation for V. This ODE for V is trivially easy to solve. Right, it is a second order ODE, and we can solve it through our usual means. We can solve it through direct integration as well. Right, so I'm almost done. I simply just have to solve the problem for V. So when we have a derivative and it's equal to 0, we know that we can just start integrating both sides. So we integrate once, with respect to t, right? So this equation looks a bit funny, but the integral of 0 with respect to t, the antiderivative of 0 is a constant. The antiderivative of the second derivative, that's just the first derivative. Now we can integrate this again. The antiderivative of the first derivative is the function itself. And when you integrate a constant with respect to t, you get that constant times t plus some other constant. Right, so that's one way we can solve this ODE for V. Interestingly, and I'll just do this as an aside, actually, no, I won't do that as an aside. You can use the normal method sub e to the lambda t, etc. Right? You will find lambda equals 0 repeated. So if you do know the general solution, which we haven't actually finished proving in the blue yet, you can actually then finish off solving this ODE. Oops. You can get V of t equals that as well. But you need to know this form, which is what we're trying to prove, actually. So we said our general solution for y was y of t equals v of t times this exponential that we sort of knew from our naive approach. And then we found out what v of t was. Which is equal to, oh, I really shouldn't use these letters because C was used elsewhere. That looks like capital C enough. Okay, so that's the form of the general solution in the repeated eigenvalue case. Note that you get a capital T times E and just a plain old E term, right? We now have two constants of integration, which is what we really wanted when we started. More formally, we have two linearly independent basis functions for this solution. Now that's a bit of a mouthful and it's not something that's emphasized in the course, but these two functions, e to the something t and t times e to the something t, they have a different functional form, right? There's a different dependence upon t, and both of those solve the equation, and you can superpose them. So the long and short is that when you've got a repeated eigenvalue case, your initial guess at a solution, your naive guess, e to the lambda t, isn't sufficient. It misses half of the solution. So you have to go back and modify your guess in order to save it. So after we modify our guess and find out what function we need to multiply e to the minus b on 2t, we find this form of the general solution. And that's it.